You know, in the world of AI, we've got these incredible tools that can generate stunning images, write code, you name it. And for years, the two most powerful ways of doing this have been seen as bitter rivals. I mean, totally different philosophies, different strengths, and some really big weaknesses. But what if that whole rivalry was just one big misunderstanding?
So that's the big question we're diving into today. We're going to look at two titans of AI creativity and uncover this hidden connection that is, and I mean this, fundamentally changing how we build these intelligent systems. Okay, to really get this story, we first have to understand the two basic ways an AI model can learn about the world around it.
So on one side, you have what are called generative models. Think of these as the artists, the storytellers. They don't just learn to recognize a cat, they learn the deep down essence of what makes a cat a cat. This really profound understanding is what lets them create brand new, totally original cat pictures from scratch. And then on the other side, you've got the discriminative models. These guys are the specialists, the critics. They are laser-focused on one job, telling things apart. They don't need to know how to draw a cat. They just need to be world-class experts at spotting one in a lineup.
All right, now let's meet the all-stars, the big names that represent these two philosophies, the Generative Adversarial Network, or GAN for short, and the autoencoder.
First up, the autoencoder. The best way to picture this is as a brilliant, almost perfect data compressor. It takes something complex, like a photo, and it has two parts. The first part, the encoder, squeezes that photo down into its most essential information, a tiny compressed code. We call this the latent space. Then, the second part, the decoder, has the tough job of trying to recreate the original photo perfectly, using only that tiny compressed code.
And then we have the GAN. This setup is way more dramatic. A GAN is basically a high-stakes game between two players, a generator, who's like an art forger, and a discriminator, the detective. The forger's only job is to create fake images that look so real they're indistinguishable from the real thing, and the detective's job? To spot the fakes. They go back and forth, training together, constantly trying to one-up each other in this crazy adversarial dance, until the forger gets so good, the detective is completely fooled.
So, let's put them head-to-head. An autoencoder's whole mission is perfect reconstruction. It uses its encoder-decoder pair to faithfully copy the original data. A GAN, though, is all about pure invention. It uses its generator-discriminator duo to dream up entirely new, realistic stuff. I mean, their goals, their methods, on the surface, they look like they come from completely different universes.
And this is where the real conflict, the big drama, comes in. Because for all their power, each of these superstar models comes with a massive, frustrating trade-off.
The bottom line is this: GANs are brilliant. They can produce these incredibly sharp, photorealistic images that just blow your mind. But, and this is a huge but, they are notoriously unstable and an absolute nightmare to train. That whole adversarial game can just fly off the rails. Autoencoders, on the other hand, are super stable. They're predictable, their training is smooth. But their output? It can often be a little blurry, a little fuzzy, and frankly, kind of boring compared to what a GAN can do.
And hey, don't just take my word for it. This isn't just a casual observation. It's a huge, well-documented problem in the machine learning community. As these researchers pointed out in a major paper, this instability is a massive roadblock for GANs. It really holds them back.
So for years, the big idea was to try and build these clunky hybrid models. Borrow the best parts from each. But then a group of researchers stumbled onto something way, way deeper. Not just a patch, but a fundamental link that was hiding in plain sight the whole time.
This is the big reveal, the twist in the story. What if this epic rivalry wasn't a rivalry at all? What if, when you look at the deep down math, these two totally different approaches were actually just different ways of looking at the exact same problem?
And that is exactly what they found. The same research paper revealed this profound mathematical link, a kind of hidden symmetry they call a primal dual relationship, between GANs and a specific, more advanced kind of autoencoder called a Wasserstein autoencoder, or WAE.
So what on earth does this secret formula actually mean? Well, without getting lost in the equations, it basically proves that the training goals of a GAN and a Wasserstein autoencoder are tied together at the hip. They aren't separate philosophies at all. They're two faces of the same underlying structure. It really is like looking at the same mountain, just from two different valleys. You see different things, but it's the same mountain.
Okay, so this is a super cool discovery for the mathematicians, but why should we care?
Because once you understand the secret formula that connects them, you can stop trying to awkwardly glue them together and you can start building truly unified, incredibly powerful hybrid models.
And the key that unlocks all of this is a technique called latent variable coupling. Remember that compressed essential code we talked about, the latent space? Well, that becomes the bridge, the meeting point, between these two once rivals.
This diagram shows you exactly how it works. You start with an input, X, and it gets fed into an encoder. This encoder squishes the input down into that all-important shared latent space, Z. And Z is the magic ingredient. It captures the pure essence of the input, and now it can be used by both the generative part and the discriminative part of the model at the exact same time.
Let's break that down, step by step. First, the encoder compresses the data into its core features. That's our latent space, Z. Then, that single Z gets passed to two different workers simultaneously. Worker A, the decoder, uses Z to try and reconstruct the original image, just like an autoencoder would. And at the very same time, worker B, a classifier, uses that exact same Z to predict what the image is, just like a discriminative model.
You see, by forcing them to share this single brain, this latent space, the AI is forced to learn a much richer, more robust, and more meaningful understanding of the data. And that, right there, points to a unified future for how we build these things.
So let's wrap this up. Why is this such a game changer? Well, first, it means better performance. We can finally get the razor-sharp images of GANs, but with the steady, reliable training of autoencoders. It's the best of both worlds. Second, it gives us a much stronger theoretical foundation. We can actually take the mathematical proofs from GANs and apply them to autoencoders, making them far more trustworthy. And maybe most importantly, it just leads to smarter AI, models that have a deeper understanding because they're forced to use what they learn from multiple jobs at once.
This discovery didn't just solve a problem, it revealed a secret family connection. It's a huge step toward bringing together the major schools of thought in generative AI. And it leaves us with one heck of an exciting question. Now that we know how to make these incredible tools work together instead of against each other, what amazing things are we finally going to be able to create?